Hello everyone, welcome to Back Garden Science with me, Miss Willett, and today we're going to talk through this experiment that you can see on the screen, which you might have seen in the thumbnails on YouTube, something a bit like this. Unfortunately, you can't charge your iPhone this way, that is just clickbait. But what you can do is you can put these electrodes in the lemons or any other fruit that is a bit acidic, and you can use that to power this little clock that I've got here. We're going to think about why that works.
Okay, so I've got a bit of acid in this beaker here. I've also got two metals. So I've got a bit of zinc, and I've also got this little bit of copper. Now I want you to go back to what you know about the reactivity series, and I want you to think about which of these metals is going to react with that acid.
The question I'd like you to have a think about is which metal reacts with the acid out of the two that I've just shown you. Is it A, just copper, B, just zinc, C, zinc and copper, or D, neither? If you're not sure, have a look back through your notes and have a look in particular at the reactivity series.
Okay, so you've had a bit of time now, so hopefully you realised that zinc will react with acid, so I'll show you that now. And you can see all those little bubbles on its surface. I put copper in there though. Copper doesn't react with acid, so we know that because it's below hydrogen in the reactivity series. So, given that, I'm going to show you something a little bit crazy now. You might have wondered, what is all this situation on top of the zinc? And so I'm going to show you. I've got a bit of copper wire wrapped around, and I'm going to now put it in the acid copper wire down, and I want you to have a look really carefully at what you can see. In particular, I want you to have a look at where are those bubbles forming. So there's quite a few bubbles here. Are they on the zinc or are they on the copper? Now, there are quite a few bubbles on the zinc, but there's also a load on the copper, which is really weird because copper doesn't react with acids, does it? This time I've connected the zinc and the copper together using a wire. And again, something a bit weird's going on, isn't it? Can you see the zinc is bubbling, but also there's a load of bubbles on the copper, which we know doesn't react with acids. So what on earth is going on?
If we zoom in, what's going on? We've got two different metals, zinc and copper, and they're connected together with a wire which has a bunch of electrons flowing through it. So that's what makes metals conduct electricity so well, is they've got a load of free electrons that can move around and carry the charge. We've also got a solution called an electrolyte, which is something that can conduct electricity, that can carry the charge. If you use pure water, so purer than what comes out the tap, it wouldn't work. If you used air that doesn't conduct electricity, it wouldn't work. So it's got to be something that can conduct electricity, like my acid or my lemon. So this is my setup, and we know that zinc is more reactive, copper less reactive. In terms of electrons, then zinc likes losing electrons more than copper, which means that when I join the two together with that wire, I've given somewhere for the electrons that zinc wants to get rid of to flow. So those electrons will go from zinc towards copper, from my more reactive metal to my less reactive metal. So that's exactly what's happening. Zinc is giving away 2 electrons, 2 because it's in the transition metal block, and those electrons are then floating off 3 to the wire and then 3 to the copper. So floating up 3 the wire, round, and then they go to the copper, which is quite happy to accept them. And the copper ends up with spare electrons that it can use to react with the hydrogen from our acid, forming little bubbles of hydrogen gas that we can see.
And I can measure the voltage, or the potential difference, which is the amount of energy zinc is pushing those electrons towards copper with. And you can see that it's 0.73 or 4, somewhere in between there, volts of potential difference between those two metals.
What would happen if I changed the metals in my cell? That's what we're going to investigate now. And we're going to think really carefully about how a metal's reactivity affects the voltage that it's going to produce. So we've got a bunch of different metals that we're going to test. So these are the combinations I'd like to use. And specifically, actually, we've already done the copper and zinc one, so we can write that in. The voltage was plus 0.74 volts. And because we've got volts in our table heading, we're not going to write that into the table itself. Now what I'd like you to do is I'd like you to pause the video, copy in the subtitle, copy in the table, and then you can use my next couple of experiments to write in the rest of your results. And with copper and iron, we instead get a voltage of 0.14, which you can add to your table. We'll go on to the third experiment down, which is our silver and our zinc. And as you can see, this combination produces an even higher voltage of 1. And that makes sense because silver is lower than copper on the reactivity series.
And if instead of zinc and silver I use iron and silver, I can see that the voltage drops again, because iron isn't pushing those electrons towards silver as well. So it's only 0.36 volts. And if I connect together silver and copper, which are next to each other in the reactivity series, I can see that actually it's only a really small voltage, it's 0.18 volts. And if I have two bits of copper, you can see the voltage is 0, because the electrons aren't being pushed either way.
So if you have a quick look, you can see the reactivity series here, just with the 4 metals that we've used in our experiment today. And you can see that zinc was our most reactive, and silver is our least reactive. And they actually produce the biggest voltage in combination. Whereas if you had iron and copper, the voltage really wasn't very big, and particularly silver and copper, because they're next to each other on a more full reactivity series, they produced a particularly low voltage. Given that, I'd like you to copy and complete a conclusion. And your starting point is this sentence: the bigger the difference in reactivity, complete the sentence. So pause the video and get that finished off. So back to those lemons. Can we actually charge a phone or our iPads with a bunch of lemons? Well, the answer is sort of yes, if you stick a load of zinc and copper in them, because lemons are a great electrolyte. But they don't produce a lot of voltage, so you need about a dozen lemons, which is more than I'm willing to use on you lot in a global pandemic, no matter how wonderful you all are. And that battery will really only last you for about half an hour. So it's not the most effective way to do things. Pay your electricity bill, folks. Now let's summarise the key ideas of the things that we've learnt today. So the first thing is that a cell requires 2 different metals joined together and also an electrolyte to complete that circuit. And the second thing we've just seen is that the bigger the difference in reactivity, the higher the voltage produced by the cell. The last thing to note is that as the chemicals are used up, the voltage drops back to 0. and that's when you end up putting them in the bins in the library to be recycled for house points. That's it from me. I hope you've enjoyed seeing a bit of actual science again. Have a nice rest of your day. Thank you for listening.